Chapter 13 is on chemical kinetics. So what are chemical kinetics? It's the study of factors that control the rate of a reaction. So studying how quickly or slowly a reaction occurs and what factors like, say, temperature or the presence of a catalyst, that sort of thing, affect the rate of the reaction. So let's start by defining what reaction rate is. We generally measure a chemical reaction rate by looking at how much the concentration of a reactant decreases over a certain period of time. Or if you're looking at a product, you can look at how a product increases over that time. When we're looking at reactants, we are losing reactant over time, so we put a negative sign out in front of the definition. For product, we're gaining it, so it's a positive number. Remember, delta means change in, so the rate is the change in concentration over the change in time. So if we look at these two reactions depicted here, we have a reaction on the left with a fast rate where A plus B are going to C, and you can see that if we use our timer here, over the course of about 46 seconds-ish, all of our reactants have gone over to products. Or we can have a slower rate, looking at X plus Y going to Z. Over that same period of time, we've only formed 3 molecules of Z, and we still have a good amount of X and Y left. But either way, the rate, change in concentration over change in time, if it happens quickly, you're going to get a higher rate. It's going to be a higher number than one that happens slowly. When we talk about rates of a reaction, we're doing it over a certain period of time. If you look over a long period of time, you're averaging what the rate is. Or you can look at the instantaneous rate by taking the slope of the line tangent to the curve at that point in time and measuring what it is. It's important to know that if you start with a certain concentration of things, so here we're looking at hydrogen plus iodine goes to hydroiodic acid. You start with a certain concentration here, about 1 molar of H2. Your rate is going to decrease, slow down over time because you have less reactant and more product around. So at first you form product more quickly, and then it slows down as time goes on until you run out of reactant. Then your rate drops to 0 because it can't move forward anymore. So there's a couple ways to measure rate. You can do the average rate, which is the change measured over a period of time. So on this graph, if we're measuring the change in hydrogen, we could take 2 of these dots and draw a line between them and find out what the rate is over that period of time. Or we can do the instantaneous slope, which is the slope of the line tangent at any one point, or the first derivative of the equation at that point in time. It's also important to note that stoichiometry is going to affect the rate. So if we are making hydroiodic acid, the slope of our line here of creating hydroiodic acid at this point is twice the slope of the line of what we're losing for hydrogen. Because of the stoichiometry, we're making twice as much hydroiodic acid as we are losing hydrogen gas. So balanced reactions and the rate of change can tell us several things about a rate, but not everything. So from the rate of any reactant or product, we can calculate the rate of consumption or production of the rest. So if you know the rate at a single point in time, you can calculate the change in other reactants and products simply by taking, so the overall rate is going to be negative for our reactants here, -1 over the coefficient for A times the change in the concentration of A over the change in time, or -1 over the coefficient in front of B times the change in B over the change in time, or for the products are defined as positive, same idea. But it only works for that particular point in time. It doesn't tell us anything about the future. We need more information to determine what's going to happen in the future. The balanced equation and a rate can get us what's happening with everything at that point in time, but we can't predict the future from that. So let's look at an example for how to think through what's happening. For the reaction given, the iodide changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds and the change in H plus concentration. So remember, our rate is going to be 1 over our coefficient times our change in I minus over our change in time. So our rate at this point in time is going to be -1 over 3, because our coefficient in front of our I minus is a 3, times our 0.868, our final, minus our initial, over our change in time, which is 10 seconds. So if I do that math, I find that my rate there is equal to 4.4 times 10 to the -3rd molarity per second. Then I can plug that in for my hydrogen. So my rate, my 4.4 times 10 to the -3 molarity per second, is equal to my coefficient in front of my H is a 2, so, and it's a reactant, so it's defined as -1/2, my change in H plus over my same 10 seconds. And so I can solve for my change in H plus. I get an answer of -8.8 times 10 to the -2 molar. So my reactant decreases, which is why there's that negative sign there. So there's the answers. Another practice question for you. You can pause the video and work this through. Make sure you have the concept. If 2.4 times 10 to the second grams of NOBR decomposes in a 2 times 10 to the second milliliter flask in 5 minutes, find the average rate of bromine production in molarity per second. So we know here that our rate is, in this case, going to be negative change in NOBR over my change in temperature times 1 over 2 because of my 2 here. And so I have my 2.4 times 10 to the second grams, and 1 mole is 109.91 grams, so I can find my moles of my reactant. So I have 2.18 moles, and it is fully decomposing, and it's in a 2 times 10 to the second milliliter flask, so that is a 0.2 liter flask. So I can find my molarity is 10.9 molar. And so my rate is going to be negative 10.9 because it fully decomposes, so it goes from 10.9 down to 0, divided by 5 minutes, so 5 minutes times 60 seconds in 1 minute is 300 seconds. So divided by 300 seconds times my 1/2 gets me a rate of 1.82 times 10 to the minus 2 molarity per second. And this is, so it's defined as a negative, and then I lost my 10.9 molar, and so I end up with a positive number. Then I want to find the average rate of bromine production. And my coefficient in front of my bromine is a 1, so this is my answer. 0.018, which is times 10 to the minus 2 molarity per second. So measuring reaction rate, we've been giving you concentrations, but you need a way to actually measure the concentrations. There are 2 ways that you can look at this problem. You can either use continuous monitoring, so find some way to continuously monitor what's happening, or if it's a longer reaction, you can take out samples of the mixture at various times, quench it, and then analyze what's still there. So ways to do continuous monitoring: there's something called polarimetry, which measures the change in the degree of rotation of plane polarized light. So some chemicals will bend light, and polarimetry is a way of measuring that. Spectrophotometry is a very common way of doing it. You measure the amount of light in a particular wavelength that's absorbed by one component over time, and you can measure the change in that. Or if you're doing a gas reaction, total pressure is another way to monitor continuously, looking at the stoichiometry related to the partial pressures. If you want to sample it at specific times, you can draw off an aliquot. An aliquot just means a small sample, and do some sort of quantitative analysis. You can do a titration, gravimetric analysis. You can do more complex things like gas chromatography, or other kinds of chromatography can measure concentrations of different components in a mixture. And there are many other ways of doing this as well.